Welcome grade 11 chemistry students to a brand new unit. We're learning about solutions and solubility. This is the first lesson. It's on concentration. We're talking about concentration in terms of moles per liter, grams per 100 milliliters, parts per million, parts per billion, mass, volume, percentages. We'll explain what these mean in a moment. So let's get started. This is concentration. So what we're going to do first is just define what is concentration. What does it mean? And in order to be able to define concentration, we have to know what solution means. And a solution is a homogeneous mixture made up of one phase. So a solution is actually made up of a solvent and a solute combined. So that's what's mixing together, both a solvent and solute mixed together. Well, what is a solvent? Well, a solvent is a substance that dissolves a solute. It is in the greatest amount. Finally, we also have a solute. It's a substance that is dissolved by the solvent. It's a substance that is in the smallest amount. So imagine you had a beaker full of salt water. Now, what is the solution? Well, the solution itself would be the salt water. The solvent would be the substance in the greatest amount, and that actually is the H2O. So H2O is the solvent because that is doing the dissolving. It's in the greatest quantity, okay? Now, normally our solvents are going to be liquid. Sometimes they're gases, and even rarer they're going to be solids. But most of the time we're going to say our solvent is going to be water. We call water the universal solvent. So what's the solute in this situation? Well, it's actually the salt. The NaCl is the solute because it's in the least quantity, okay? So to increase the concentration of solution, what I have to do is to increase the concentration, I actually have to increase the amount of solute relative to the amount of solvent, okay? So basically, there's two ways we could do this. You could add more NaCl, and the concentration would go up because I'm increasing the amount of solute. Or I could actually decrease the amount of solvent. Just imagine taking like a drink of salt water after you've boiled off a lot of the water. There's still going to be the salt in there, less water, so it has a higher concentration. So one way we can represent concentration is by something called parts per million or parts per billion. If you look at the side of a water bottle, you'll actually notice that it says parts per billion or parts per million on it. And what it is it's the concentration of very small substances, okay? It can be expressed in parts per million or parts per billion. And they're usually what we call mass per mass relationships. So the mass of the solute is in, the amount of the solute is in terms of grams, and the mass of the solution is in grams as well. So parts per million does not refer to the number of particles, but it refers to the mass of the solute compared to the mass of the solution. So I'm going to show you the two examples. Sorry about the jumping all over the place, but I'm going to show you the two examples of parts per million and parts per billion now. So to find the concentration in parts per million, what they do is they find the mass of the solute and they divide it by the mass of the solution. Now generally the units have to be the same for both of these. So if you have grams on the bottom, you're going to need grams on the top. If you have kilograms on the top, you're similarly going to need kilograms on the bottom. It doesn't really matter as long as you have the same units. Then what they do is they multiply by 10 to the 6. And 10 to the 6 is basically a million, okay? So one thing we also want to remember, and this is kind of a hint, that once you get like 16 parts per million, it's unitless. But 16 parts per million, or 1 part per million, sorry, not 16. 1 part per million is actually equal to 1 milligram dissolved in 1 liter, okay? So parts per million are equal to milligrams per liter. Parts per billion is exactly the same, except you use it for smaller numbers. So parts per billion is for smaller concentrations, okay? So small concentrations. And the way we find it is similarly mass of solute divided by mass of solution. And what we do is we multiply by 10 to the 9. So that represents a billion. 9 zeros is a billion. Okay? So the relationship between 100 parts per million, just so you know, this is not too critical that we understand, but 100 parts per million is equal to, if I get this right, 100,000 parts per billion, okay? So it's an order of 1,000 times difference between these two things. But you use parts per billion for smaller concentrations. For example, your water bottle, you'll have very, very small concentrations. Okay, so I'm going to go over this example here for parts per million and parts per billion. So mercury poisoning can be observed in humans when you have 20 milligrams in your body, okay? It accumulates in your brain. Your body gets rid of it, but once you get 20 milligrams, you essentially go crazy. So it says express this amount as parts per million for a 60 kilogram person. So what you would have to do is, first of all, we write down parts per million, and we have 20 milligrams because that's our solute. Mercury is our solute that goes on the top. And we have 60 kilograms, that's the weight of the person. So what I'm going to do with these two values here is, first thing is I'm going to convert them to the same units. So I turn them to grams. So by doing some unit cancellation, I get 0.02 grams on the top and 60,000 grams on the bottom. We then multiply by 10 to the 6 because this is parts per million, and the answer you get is 0.33. So 0.33 parts per million. The same thing would happen if you did parts per billion. The only difference is that you're going to multiply it by 10 to the 9. And the difference is 1,000-fold. So it's 0.33 parts per million, but it is 330 parts per billion. And this is essentially how you find parts per million and parts per billion. We're not going to focus on this too much in class. We'll do a few questions in class tomorrow, but this isn't the most critical measure of concentration. Another way that we can measure concentrations is something called percent concentrations. One is called mass volume percent. Another one is mass percent. Okay, this should say mass percent. And then another one we have is volume percentage. Okay, which is what we actually use in alcoholic beverages. I'll explain. So these are the three equations that you're going to write down. You can pause the video and take a look at them. But the first one is percent mass over volume, mass of solute divided by the volume of solution in 100 milliliters times 100%. Same thing, we have our percent mass by mass of solute divided by mass of solution times 100%. And finally, we have percent volume over volume, volume of solute divided by volume of solution times 100%. These all share something in common. They all have solutes on the top and are being divided by the solution on the bottom. The variation is like it says here, mass is on the top, volume is on the bottom. Mass is on the top, mass is on the bottom. If you're using mass, you want to make sure that you have the same units. And that's it. So let's do an example of this. We're just going to do one quickly, and we'll do some more examples in class. Okay, so you have a silver ring you want to buy for your boyfriend or your girlfriend, and it weighs 6.45 grams. And you want to know actually how much silver is in there. It says sterling silver. Now, when you Google sterling silver, what it will say is that it's actually 92.5% silver. If it was more than this, then the silver would be really soft. Like 100% silver is very, very soft. So they have to actually put other impurities in it to actually make it stronger so you can make jewelry out of it. So we know that 92.5% of this compound is actually sterling silver, and we have 6.45 grams. So what is the solution? What does this 6.45 grams represent? Is that my solute or is that my solution? Well, it's actually your solution because that's the mass of the whole thing. And our solute is actually the silver, and that's what we want to find. So what we're going to do is we're going to actually solve for this, and we're going to put the mass of the solution in here. We want to make sure that our units are the same, so we have grams there, and we're going to put a percentage in this. So let's just substitute our equation, or these numbers, into our equation. So next what we're going to do is we're just going to do some simple algebra where we rearrange this equation and we solve for mass of solute. Since 6.45 grams is being divided on this side, that means to eliminate it, we have to multiply it on both sides. It's going to be multiplied on this side, and it will be removed from here. 100% is being multiplied on this side, so on the other side it's going to be divided. So it will look like this. So when you actually do the math, the percentages will cancel out in terms of units, and you get your units in grams. And our answer is going to be 5.97 grams. So in 6.45 grams of sterling silver, there is 5.97 grams of silver. So that's how you would use these equations. Okay, you can do it similarly for mass volume percent or volume percent. We'll do a few examples in class tomorrow as well. So now we're going to talk about the most useful unit of concentration, which is called molar concentration. And what it is it just involves moles. So the equation itself is going to be C, which stands for concentration, equals N divided by V. Now you know the units for N already. It's going to be moles. And you also know the units for volume, hopefully. It could either be milliliters or liters, but in this case we use liters. So the units for concentration will be moles per 1 liter, okay? Or another way we write it is actually just big M, which is moles per liter. Molar concentration, or molarity sometimes, that's what it's called. It's useful as it's related to the number of particles in solution, which is the mole concept. And this allows us to solve problems involving quantities in a chemical reaction. So for example, we have a saline solution which contains 1.9 grams of sodium chloride. Sodium chloride is dissolved in 100 milliliters of solution. What is the molar concentration of solution? Well, to answer this, we look and we say, okay, concentration equals moles divided by volume. What do we know in this question? Just like all our other questions, what we're going to do is we're going to look for the numbers and we're going to determine what they represent. And you have to know that grams is going to be mass, okay? So that's 1.9 grams. And then I look at this guy and I have volume because that's milliliters. Now, when we actually look closer, we say, all right, so what do we have? We have volume. That's it. Okay, sir, I can't solve for concentration. I don't know it. Well, we also know mass, and we know from our previous unit that we can convert this to moles by dividing it by the molar mass. So that's actually what we're going to do. We're going to take our volume, convert it to liters, take my mass, convert it to moles, and then substitute in. So the first thing that I'm going to do here is find the molar mass of sodium chloride, because that's what I have. 1 sodium, 1 chlorine, 22.99 plus 35.45 equals 58.44 grams per mole. Now we have 1.9 grams. So clearly we do not have 1 mole. To find a mole, what we have to do is we have to take our mass and divide it by the molar mass. Okay? I'll show it like this. So I'm going to take my mass, 1.9 grams, and I divide it by the molar mass, which is 58.44 grams. You can see this is the same as division. Grams cancel out, and we get our answer, which will be a whole lot less than 1 mole. So now when we look, we actually have our moles as well. Our moles are 0.033 moles. We had volume before. One thing that we have to check for is that we have to make sure that our volume is always in liters. So what I'm going to do to my milliliters is I'm going to convert it to liters. So for every 1 liter, there is 1,000 milliliters. In our calculator, that means that we're going to divide 100 by 1,000, which is equal to 0.1 liters. So now we have our volume, we have our moles, we can just substitute in. So C equals N divided by V. It's actually little c. I know it looks like a big C there, but it's actually lowercase c. And our moles are 0.033 moles. Okay. My volume is going to be 0.1 liters. When we divide this, we're going to get a concentration of 0.33 moles per 1 liter. Okay. Or you could also write this as 0.33 capital M. Capital M means moles per liter, okay? And that's our final answer. Therefore, the concentration is 0.33 moles per liter. Okay, I'm going to leave you with this question, and I'd like you to try and answer this for me tomorrow. So it's an extension question of what we've been doing, and I'm going to walk you through how to set it up, and you should be able to solve it. You have a solution of calcium sulfate. It has a concentration, which is a molar concentration. So we have C equals 0.0153 moles per liter, capital M, or moles per liter. A student takes 65 milliliters of the solution and evaporates it. What mass in grams is left in the evaporating dish? Well, we just write down what this is here as well. It is volume in milliliters. So what I'm going to need you to do is you're going to have to convert this to liters. Okay. If we take a look at our equation and we check off what we have, it says we want to find a mass. So mass equals question mark. I don't know that. So we know my concentration. We will know my volume. How am I going to find the mass? So you should be able to convert to mass. Again, using the molar mass. In this case, you're going to multiply by the molar mass. If you're not in my class, molar mass can also just be represented by 1 capital M, not 2. All right, so if you have any questions, please let me know, but you should bring this question to class tomorrow. Enjoy.